In this lesson, we're going to be talking about different types of intermolecular forces and their relative strength among one another. So before we jump into that, let's think of a few concepts here. We have water at liquid at room temperature, and you may have wondered at some point why water is a liquid at room temperature and what really holds water molecules together. If I take an example of water cup has suppose about half a liter of water in there, and you have about gazillions of water molecules in there, and you have all those water molecules staying in the condensed form or the liquid form and not leaving in the form of vapors. So that's something will be answered as we move along here. And the second question you may want to ask yourself is gasoline, which has the active ingredient octane, is more volatile, which means it evaporates or it has a low boiling point, than water, which is relatively non-volatile, which has a higher boiling point. So all really depends on how the molecules are held together with the help of these intermolecular forces. So let's focus on the first type of intermolecular forces. The first one is called hydrogen bond, and I usually talk about hydrogen bonds first because it's the most easiest one to recognize. And and the factor that you have to look into in order to recognize the hydrogen bond must have a covalent bond or must be covalently bonded to either fluorine, oxygen, or nitrogen. You may not have to have all necessary three of them, but just one atom is fine at a given time. So the acronym for that is just FON. So if I take examples of compounds that makes hydrogen bonds, that would be HF, H2O, NH3, and I can probably just talk about CH3OH and so on. So what we really have common in all of them is we will have hydrogen making a covalent bond with either one of those three most electronegative elements, whether it's a fluorine or oxygen or a nitrogen. So that's the criteria you're going to be looking for. And also keep in mind, just because you have a hydrogen and one of those electronegative atoms in the molecule, that doesn't necessarily mean they're going to be directly bonded with one another. So you may have to look into their electron dot structure or the Lewis dot structure to clarify if hydrogen is directly bonded with one of those three elements. Now, how that really works, it creates a so-called and a very strong permanent dipole. So if I take an example of HF, so the bond, this is how the Lewis dot structure is going to look like. Now if I compare the electronegativities, hydrogen is very less electronegative than the fluorine, so as a result, shared electron is going to be more toward the fluorine, and as a result fluorine gets a partial negative charge and this hydrogen will have a partial positive charge. So that actually creates a permanent dipole. And same story with maybe another HF molecule that's going to be close by. So this HF molecule that's close by will be in a very similar environment. Okay, so since they are in a very similar environment, you can clearly see how you have a partial negative charge and a partial positive charge created on actually the same molecule here. So you make these interactions between the partial positive and partial negative, and this particular interaction would be called a hydrogen bond. So it's a strong permanent dipole because it's always going to be there. You don't really have to do anything to create this dipole altogether. And if I take another example maybe here, and I can just talk about water. In water, the structure looks like this. It's a bent molecule where oxygen is more electronegative, and since oxygen is more electronegative, the bond pair that's shared between oxygen and hydrogen is going to be more toward the oxygen. As a result, oxygen gets a partial negative charge, and both of these hydrogen will have a partial positive charge. Okay, so now if I have another water molecule close by, it will be in a very similar environment. Okay, so we'll have a partial positive charge on the two hydrogens and a partial negative charge on the oxygen. So as soon as you create that, you can see here how this oxygen of one water molecule and the hydrogen of the other water molecule will have a strong attractive pull between one another because of this partial positive and partial negative charge, and that's what creates the hydrogen bond. So that's going to be another example of a hydrogen bond there. Okay, so in this particular case, both HF and H2R are both hydrogen bond donor and acceptor. So think of that. You have to have a fluorine atom. You have to have one of those three atoms in the acceptor. In this particular case, I can clearly say this fluorine is acting as a hydrogen bond acceptor, and this hydrogen is going to be a hydrogen bond donor. So the two conditions you must have in there, obviously hydrogen bond must have a covalent bond with either fluorine, oxygen, nitrogen, and the second condition, your hydrogen bond acceptor must be either fluorine, oxygen, or nitrogen. So it's the same thing basically in both of those cases. Okay, so that's your hydrogen bond. Let's talk about the second type, which is going to be the dipole-dipole. Now, the dipole-dipole is created between polar molecules, the molecules that are going to have a net dipole moment. So they will have so-called a permanent dipole, but it may not be as strong dipole you would actually see in case of hydrogen bond. All right, so keep in mind both hydrogen bonds and dipole-dipoles are created between the polar molecules. You just have an extra polarity in case when the hydrogen bonds are being made, just because of the really high electronegativity difference between the hydrogens and those fluorine, oxygen, and nitrogen. Now, if I have a polar molecule, and I can take maybe some examples here, I can talk about maybe H2S, I can talk about HCl, or I can talk about HBr, or I can talk about maybe another molecule where CHCl3. As long as you have a net dipole in the molecule, it will have the potential to make a dipole-dipole moment. Now, if I take an example of maybe HCl, so in HCl, this is how the structure is going to look like. Chlorine is more electronegative than hydrogen. As a result, chlorine gets a partial negative charge and hydrogen gets a partial positive charge. And if I have another one of the same molecule close by, it will be in a very similar scenario where chlorine will have a partial negative and hydrogen will have a partial positive. And now you will have these interactions between the chlorine of one molecule with the hydrogen of the second molecule, and those are going to be your dipole-dipole interactions. Okay, and obviously they're different than the hydrogen bonds because of just the extent of the polarity, or just the extent of how strong the dipole is. Let's take another example here. If I have CHCl3, for example, this one right there. So in CHCl3, when I draw these molecules, chlorines being partial negative, this chlorine being partial negative, this chlorine being partial negative because carbon is less electronegative than the chlorines, and hydrogen being the bond between the carbon and hydrogen is always going to be considered nonpolar. So there's not going to be any partial positive and partial negative between the hydrogen and the carbon. So that's something you want to keep in mind. And if you have a hard time understanding the polarity and the polar bonds, you want to watch another video where I have discussed about electronegativity and the polarities. So this carbon is going to have partial positive because of the chlorines having partial negative. Now, someone may argue that this left dipole and the right dipole, they're going to be canceling one another, and that's going to be fairly true. I can have this dipole going this way and this dipole going this way. So they may cancel one another out, but then when I look at this bottom dipole, you will have nothing canceling that. So there is a net dipole in the molecule. So since there is a net dipole, you can have another molecule close by, and they will be attracting, they will have an attraction between the partial positive carbon and the partial negative chlorine with one another. Some other examples going to be molecules that contains oxygens. For example, I can talk about CH3, C double bond O, CH3. So in this particular case, the only bond that's actually going to be polar is going to be this carbon-oxygen bond. because oxygen is going to be partially negative and carbon is going to be partially positive. The next one is the London dispersion forces. In London dispersion forces, you don't really have any net dipole. They are going to be made between the nonpolar molecules. So any molecules that's left behind is going to be making London dispersion forces. So I can talk about CO2 or CS2, or I can talk about C2H6, any hydrocarbons basically, CCl4. I can talk about CBr4. You may very well have polar bonds, but you have to look at the molecule overall. So if the molecule overall is nonpolar, they are not going to be making any dipole interaction. They will be making only London dispersion forces. So all diatomic molecules, they're going to be making only dispersion forces. The key on making the dispersion forces is the formation of instantaneous dipole. There's no permanent dipole like you have seen in the other two cases. So what really happens, if I take an example of maybe helium, so helium has only 2 electrons. So suppose this is the shell we're talking about in case of helium, the first shell. Okay, so I will have 2 electrons in there. Okay, so and obviously there is going to be a nucleus at the center. So that's electron here and that's electron here. And for the most part, they're going to be far away from one another, so there is no creation of the dipole in there. But momentarily, what would happen when these electrons kind of going around the nucleus with high speed, there is a good chance that they will both be on the same side at a given point. So if that becomes true, like let's say this is one electron and that's another electron, and they do come on the same side at a particular time, then you create this side, the left side here, to be partial negative, and then since you don't have an electron onto the right side, that creates a partial positive charge. So that's what the instantaneous dipole going to be. So once you have an instantaneous dipole, it will help create an instantaneous dipole with another helium molecule that's going to be close by. It may create a instantaneous dipole just like this. So where you have an electron here and an electron here. And as a result, this will have a partial negative charge and this will have a partial positive charge. And just a momentarily creation of this dipole and momentarily creation of this positive and partial negative, you will see some interactions there, and those are going to be your dispersion forces. Okay, so they are going to be actually the weakest out of all of them, and I'll tell you the order in a little bit once we talk about all of them, but they are going to be the weakest because they are instantaneous dipole and they are not going to be there all the time. It's not permanent. Okay, and keep in mind they are going to be created between only nonpolar molecules. So if you can figure out the polarity of the molecule, that solves a big problem in terms of figuring out the intermolecular forces. Okay, so then the other type you will see is called an ion-dipole interactions, and this is mostly going to be seen in like when you take a gen chem, may not necessarily see in organic chemistry, and mostly when you dissolve something in water. So suppose I have an ion. So ion could be anything, either a cation or an anion, and there isn't a molecule that has already in a net dipole, or there isn't a permanent dipole in the molecule. So that would create an ion-dipole interaction. So when I dissolve this NaCl into water, this is going to exist as Na plus and Cl minus in the water. So as a result, what happened, I know the water molecule already have the polarity in there. The oxygens already have a partial negative charge, and the hydrogens already have a partial positive charge. So what's going to happen, I can have the chloride here that you just kind of broke into the NaCl into sodium and chloride ion. So as a result, they will create this ion-dipole interaction. So in this particular case, and clearly see, okay, maybe this partial positive on the hydrogen and the full negative charge on the chloride, that's why it's going to be an ion-dipole, will create a ion-dipole interactions there. So obviously you could have multiple water molecules around the chloride here, but for the sake of simplicity, I'll just kind of draw only a few of them here. Okay, so they can all have these ion-dipole interactions there. And you don't only have to look at the interaction of the chloride with the water, you could literally look at the interaction of the sodium as well. So obviously when you're looking at sodium, it's got a positive charge, so it's going to be attracting to the negative or the partial negative of the water, which is going to be oxygen that's going to be bearing it. So this is how it's going to look like. You got a partial negative on the oxygen and partial positives on the hydrogens. And I can probably just try another one down onto the opposite side. And like I said, you will have a multiple around the sodium and multiple around the chloride. I'm just going to show only a few of them here so that I'm not making this slide too busy. Okay, so then it's going to create between the partial negative oxygen and the full positively charged sodium, there are going to be interactions, and those are going to be called ion-dipole interactions. Okay, so moving along, then you may very well also see the ion-ion interactions, and that would obviously happen when you dissolve something in water for the most part. You may also see ion-ion interactions if you dissolve in different other solvents, but mostly we talk about water. But like I said, it's not limited only to the water. So you would have NaCl and broken into Na plus and Cl minus. So when they are in the solution form, this Na plus and Cl minus, even they are actually separated from one another, but they could still show some interactions even in when they are in the solution. So those interactions that you will see in the solution are going to be called the ion-ion interactions. So don't take those as an ionic bond. The ionic bond is seen when you actually have a solid. Like when you have an NaCl solid, that's when you have an ionic bond. But once you put them into a solution and has been broken up into Na plus and Cl minus, now all it's really going to show is the interactions. So those are called ion-ion interactions. So you must have a cation and the anions, and obviously they're not only limited to the Na plus and the Cl minus. As long as you have, a positively charged ion and a negatively charged anion, you will be able to see an ion-ion interactions. So in terms of their strength, so obviously when you have a full negative and full positive charge and those ions are interacting with one another, that's when you're going to get the strongest force because two oppositely charged ions attract one another. But on the other hand, when you're looking at, suppose this dipole-dipole, there's not a full positive or negative charge. There are partial positive and partial negative charge. So as a result, they're not going to be as strong as you would see in case of ions. And same story with the hydrogen bonds. They don't have a full positive and negative charge. So when I'm looking at the strength here, your weakest intermolecular force is still going to be the dispersion forces. Okay, followed by dipole-dipole are going to be stronger than your dispersion forces, and then your hydrogen bond is going to be next, and after that you got ion-dipole, because think about in ion-dipole you have one with full charge and one with just a partial charge, so ion-dipole interactions, and your strongest in going to be ion-ion-dipole interactions. Okay, so among those five, you may see obviously all five of them, but when you take a Gen Chem, you are going to be looking at ion dipoles as well, and maybe ion-ion as well. But when you're looking at when you're taking organic chemistry, for the most part, you're probably going to be limited to the first three types. Okay, especially in covalent compounds. So those are the three you're going to be seeing for the most part. All right, so in among those three, hydrogen bond is going to be the strongest, and the dispersion force is going to be the weakest. And obviously, when we're comparing those, we're just kind of relatively comparing those. You may have to look at some other factors, such as the molecule's molar mass and how big and how, in terms of surface area, how big or small the molecule is as well. Now, I will talk about in a different lesson. I'll give you a few examples where you're going to be learning how to determine the boiling point and how to determine the vapor pressures based on these interactions. So now, if I go back and and answer my question here, where I talked about why water is a liquid at room temperature, that's because water actually makes hydrogen bond, and why octane is a volatile. So octane comes in the category of an hydrocarbon, so it's going to be C8H18. So if I probably just go back and write it up there. So water being making the hydrogen bonds and octane being C8H18, and that's just going to be dispersion forces. Since the dispersion forces are going to be the weakest and they're going to be easiest to break, so that's why you can break the octane molecules easily, and it makes it volatile as compared to the water, where you have stronger intermolecular forces and it makes it a non-volatile. So I'll have another video where I'll talk about different examples and how you're going to be figuring out the boiling point and the vapor pressures. All right, hopefully if it was helpful video. If you have any questions, feel free to leave any comments below.